Okay, yeah, I wanted to make a little video talking about, you know, gears and when it makes sense to actually use gears. Um, Here's an arbitrary stepper motor, for example. Now, it doesn't always make sense to use gears. Um, like, for example, let's say we had wanted to run this motor at 10,000 pulses a second, and we wanted a 2-to-1 gear ratio. Well, again, you can kind of see that, this is roughly, probably about 20 or 30, um, you know, newton meter or meters um, on this. But if we ran like a 2-to-1 gear ratio, that puts us down here, okay, which is about 100. Okay, so so you're talking 20 or so versus 100 for only a doubling, of your gear ratio. So you're only getting double the torque and half the speed. So, but on the other hand, you're not getting anywhere near the torque you get if you just slowed your motor down to 5,000 RPM. Now, if you took your motor and ran it at, um, put a gear ratio of 10 to 1, okay, well, from 10,000 RPM, you'd be down to 1,000 RPM, but, you'd be at like 200 on the torque. Okay, so, but the problem is at 1,000 RPM, you'd be way up here instead of 200. You'd be at, like 500. So, now, so gearing really doesn't make sense in any way, shape, or form here because you're always going to be lost, and that's on top of, this isn't even taking into account the efficiency loss you might get, and assuming like 90%, so you'll have that as a further speed reduction or whatnot in your motor. But now if you load it down, let's say 4,000 RPM, okay, and you did a 2-to-1 gear ratio, well, it puts you down here, and again, we're like, about like 120, so it'd be like 240, if you drop from, with a 2-to-1 gear ratio from 4,000 down to 2,000, so again, that's roughly the same place you would be. So again, there's no advantage in a 2-to-1 gear ratio. Now, let's say you did a 4-to-1 gear ratio, so you dropped it down to 1,000. Well, instead of being, that'd be like 480. Okay, so but you go down to 1,000. Well, that's roughly where you're going to be. So again, there's really no advantage to using a gear train here either, unless you want to go to a much higher gear ratio, like 10 to 1. Okay, so instead of being 4,000 pulses a second, it'd be 400. Okay, so instead of it being like 280, it'd be 2,800 on the torque. So, and nowhere on this curve does it ever go up as high as 2,800. So you're talking 400 pulses a second puts you around here, and again, the max you're going to get is like 700 or so at that point. So there is an advantage at that point, to going with a 10-to-1 gear ratio. It starts to make sense if your ratio is high enough. Now, if we go and look at, like, say, the 2,000 RPM point, all right, we're pulling in at, just under, like, 300. So let's say 280 or something like that. Well, if we do a 2-to-1 gear ratio, it's going to be like 560, right? Well, that's a slight advantage because we're only at about 500 here, maybe a little less than 500 at 1,000 RPM. So now it's starting to make a little bit of sense. There's a little bit of an advantage, and that's probably, it'd probably be about the same when you consider the efficiency loss. But again, it's starting to make more sense now. But now if we do a 10 to 1 at this point, again, 280, 2,800, is what we get. But at 200 RPM, so or pulses per second rather, that puts us down in this neck of the woods. Again, nowhere on this curve are we at 2,800. So my point is that it starts to make more sense. And if you do it at 1,000, okay, well 1,000, we're at like 500, okay, and you do it a 2-to-1 gear ratio, well, cutting it down to 500 pulses per second, would be at 1,000, and nowhere we don't come to anywhere near 1,000. This peaks at about what 750 or something like that. So there's already an advantage, even starting at 1,000 or pulses per second, let alone going to 10-to-1 on the gearing ratio, which you're at 5,000. You're only running at 100. Equivalent pulses per second, but we've got a 5,000 torque rating at that, and you couldn't even run a stepper motor at around that speed because you'd be in the resonance area. So it's going to behave capriciously. So at some point, if you're wanting to run your stepper motor pretty low, it makes all the sense in the world to use gearing because of that resonance problem and the fact that you see your torque drop off. Now, this is basically a unipolar motor that's, as you can see here, wired essentially as a two-phase motor, essentially, because they're actually using two phases at a time, I guess is what they mean. Because they call these, on this data sheet, they call this two-phase for some reason, just like a bipolar motor is two-phase. But in any event, if you go down here, as these numbers, increase, so this is a higher voltage motor, but lower current, and this is a high current motor at lower voltage, but the exact same torque, and you can see it here. You see here the different currents it runs at, for the different motor series, and you can see the torque is exactly the same in all three of these cases. And this is a bipolar motor, and it's got a different torque, obviously, but as far as these unipolars, they're the exact same holding torque, but you can see the different loading curves they have. So there is an advantage to using low voltage, high current motors as opposed to high current, or low current, high voltage motors. So, because you can see that this curve is a hell of a lot better. I mean, it makes more sense, to even the 10,000, case to gear from 10,000 pulses per second. Let's say we did a 2-to-1. Okay, well, this is like 150, so that'd be like 300 at 5,000. Well, that's about equivalent, even at this high pulses per second. If you remember down here, if we did that thing, well, geez, I mean, there was no comparison. This is like 3 times. You're 3 times. You're way better off just using the motor and no gearing rather than gearing in a motor. But here, it's about a break even. So, let alone if you did a 10-time ratio. Now, if you did a 10-time ratio, okay, we got like 150. That would, 150 times 10, is 1,500. At 1,000 RPM, but again, 1,500 is nowhere near on this curve. So that makes more sense. If we go down to the 4,000 case, well, hell, we're already at a little over 400. Let's just say 400 for the sake of ease, and we cut it down to 2,000 pulses per second. Well, that's going to give us 800. And really a little over 800 as opposed to it being, 650 or so. So there's already an advantage there. And then if you do the 10-to-1, well, okay, it's 4,000, running at 400. So instead of, topping out at 700. So, I mean, again, you're starting to see that gearing makes sense. And a 10-to-1 ratio, would be still fairly efficient. It would take... as a matter of practice, generally about 2 gear steps, to produce that, because otherwise, let's say you've got a 1 centimeter diameter gear, okay, or let's just say really 1 centimeter radius, as the case may be. You go up to, a 10 centimeter radius. That's a 20 centimeter gear. It's a huge gear, okay. And even if you started with a 1 centimeter diameter, it's still a 10 centimeter diameter gear, and that's still like 4 inches. So normally it's going to be a little impractical, and certainly you could do a smaller smaller gear, but at some point you're running into, you know, a loss of strength and everything else. So, you know, you have to have a certain size, but it depends on what you're trying to do. If you're after torque, high torque, well, you know, you're still going to want your pinion to be, you know, somewhat beefy, you know what I mean, depending on how much overall torque you're talking about. But at any rate, you know, that's just how a stepper motor works. So now when you talk about DC motors, you know, you kind of have a load curve more like this. It's usually pretty linear. So, you know, we got our motor speed and our torque. So, and, you know, there's an even trade-off of 50-50, and here's our peak efficiency point, which occurs at half speed and half torque. I mean, our peak power, and then our peak efficiency, you know, occurs at, you know, about, you know, what, 10 or 20% of the torque and about half the speed. So, you know, and like I said, this is, you know, where they normally rate the operating point to be. In other words, you know, modest speed but low torque. So, you know, because here you can see the current, you know, goes up, you know, as your torque increases. So, you know, and this is what, you know, you might term an LRC, you know, a lock rotor current is was traditionally termed, but the stall current or whatever is another, you know, name for it. That's what they got called here. So, but you can see the current goes up, you know, but it reaches a peak maximum, which is determined based on the resistance of the motor. So, you know, that's its maximum current at stall. So, you know, for a given voltage. But anyway, you can see this is a linear curve. So, you know, if you took this, for example, you know, it's 50% speed, and we can say the torque at this speed, you know, since this doesn't have any measurement here, we can just say it's equal to 1. Okay, that's 1 unit of torque. If we were running at a peak power and we put a 2-to-1 gear ratio in it, where our speed would be cut in half, but our torque would be double. So, I mean, it pretty much puts us at the same point we would be, you know, on this curve, you know, because again, we just cut the speed in half, okay, but we've doubled the torque. Well, that's exactly where we would be on this. Well, that's not where we would be. You know, if we cut the speed, you know, down to, I mean, the torque, if we doubled the torque, okay, you know, the speed would be down to pretty much 0, or, god damn it, you know, the speed would be maximum here. See, I'm kind of confused because this is not the orientation I'm used to on this curve. It's got me kind of confused. You know, because normally I see speed down here and torque here, so I'm a little bit confused. But anyway, the point is, though, is that, you know, you double your torque, but, you know, if you double the speed, so in other words, you know, a gear ratio of 2-to-1, though, you know, would, you know, let's say this is like 600 RPM on the speed, you know. So if you did a 2-to-1 ratio, you'd end up with 300 RPM, but you would double the torque. So, whereas on this curve, just by adjusting the motor loading to where you get double the torque, okay, you know, you'd end up with 0 speed. But here you actually end up with, you know, still with like 300 RPM with double the torque. So there's an automatic advantage to gearing here. So, you know, whereas again, you know, this curve represents, you know, at a fixed voltage, okay, you know, if you actually stall the motor at a fixed voltage, this is going to be its current, and this is going to be its torque. It's maximum torque, but 0 rotational velocity. You know, whereas the other end of the extreme is, you know, no torque pretty much, but maximum speed, but, you know, a no load current that's not quite 0. So, you know, the point is that as you load the motor, you know, with a greater and greater load, you know, you traverse this curve as your torque increases. Your torque requirement increases, you know, the more towards stall you drive your motor. So that's where this comes from, but it's a trade-off between speed and torque. So again, the less torque you need, the higher your speed. But what if, for example, you actually just wanted your motor to actually run at a lower speed and have a higher torque? Well, if we did that, starting with this operating point here, we ran it at, with a 2-to-1 gear ratio, it would be half the speed, okay, and so instead of 600, it'd be 300 RPM, but it'd be double the torque. And again, prior to that, the only way to double the torque is to cut the speed down to 0, because we start with this torque of 1, okay, well, we'd have a torque of 2 here, and torque of 0 here, because remember, it's linear, so it's, if we just normalize it to this operating point, that's what we get. But now if we did a 10-to-1 gear ratio, this makes it a little more clear. Well, we'd have 10 times the torque, but instead of it being 600 RPM, it'd be 60 RPM. So we wouldn't have 0 speed, but we'd have 10 times the torque. Again, minus the efficiency loss, of course. But, the point is, that's kind of how gearing works, But again, looking at this, it almost always makes sense with a DC motor, to use gearing. But with a stepper motor, that's not necessarily the case. So, that's what I was trying to say, is that a stepper motor, it doesn't always make sense to use gearing. Sometimes you're better off just simply reducing the speed of your motor to get higher torque, because it's a non-linear curve. So, anyway,